Hi everyone, this is ME 67050 thermoelectric material. Today is Wednesday. Let me see. Next week we have midterm. Today is 22nd. Next week is 29th, Wednesday. So we have schedule. Next week we have a midterm. Today I'm going to I don't think I'm ready for overview for the exam, but I tried to give an overview. Okay, some homework problems. Okay, mm, we were talking about electron physics and then move on the transport property of thermoelectric. I think last hours, but still, I think this midterm I'd like to include the electron physics and the basic, yeah, some related homework problem up to transport property. Okay. So I think the one of most important feature of electron is the electrons orbit around the. Let me see. Yeah, this is an atom, and electrons. This is a proton. Nucleus, and it is, we believe, orbiting. And then we learned there is quantum number, possibly so quantum number 1, quantum number 2, quantum number 3, etc. Okay, so this is a very important. We understand this. Even hydrogen, one proton and one electron. The electron can depend on the energy. This is energy level. It can be a second quantum number if they absorb the energy. Okay, photons or thermal energy, whatever. Usually the photons, and then it can jump to a higher level. So interesting is once it goes a higher level, also sometimes it can back to lower level, and then energy, the energy is the wave, no, the frequency. Okay. So exactly the exact energy is emitted when it's back to the lower level quantum number. So it is very interesting. There is this is energy is discrete. That's what we understand. Discrete, which means either this level energy or this level energy, or between these there is a nothing happen. Okay, so they have to have exact energy so that they can jump or back, and then exactly there's energy conservation. So this basic electron the physics is so important. Okay, even I would say the universe, the creation of universe is basically like that. Okay, so the most of physicists believe in the beginning there is a big bang and then universe created. Okay, so what is a big bang is there was a no mass but the energy, big energy, then create the particle. They create the particle in the beginning, big bang, some quark and electron. Electron is fundamental, and some quarks. So they forms and they create the proton. This is proton. So they try to create the proton, but still there is there was energy, but nothing we can see in terms of our physics. And then after a certain time, they forms a hydrogen. Okay, that's very interesting. Once the proton and the one electron, and then it goes like what we said. It's a quantum number 1, 2, and then energy coming out. So this light energy is we call first time it ever seen the light is, I think, a microwave background, something like that. That was the first after Big Bang. So we can explain that about this. Once it forms, it takes time from the Big Bang to first the hydrogen forms, and then the microwave background we found it because of that. Because of that. So that's why I'm telling you, all the origin of the universe we can explain just the electrons physics. Laser, I told you, laser we can explain is everything is like that. Okay, and the light, the spectrum, everything is that. Colors, rainbows, colors, spectrum is that. So some of the homework problem, why diamond is transparent? Why the copper is reddish? We can explain that. I think you have a look at. And one of another homework problem was parser. There was a, I think I'd like to look at it. What was the number of homework parser? Do you remember what number? No, no, no. 16. Should be 16. Yeah, this problem. Yes. Most energetic rotating parser in universe is discovered to emit the Fermi energy of about 10 to the 8. It is given electron volt, billion times more powerful than the visible light. So powerful. Astrophysicists estimate the energy by assuming that the sun of radius 700,000 kilometer and the mass something collapse to parser. When as the sun collapsed to a small radius, then this kind of energy coming out. So we something we can look at, and then when we the Fermi energy and the sun and sun mass and assuming one proton mass and then how many proton and then when we calculate something we come up with the energy 4 times 10 to the 8. Okay, you can look at it 4 times about 10 to the 8. So that parser is neutron. Okay, neutron star, something like that. That's what we assumed using this. So I don't want to go detail, but something like that. And um, what was it, 17? Yeah, and 24. Diamond. Yeah, let's. The diamond is transparent. So this is just wavelengths. This is micron, 0.3. So about this is about visible 0.7. This is all we can see. Violet and red. This is red. This is ultraviolet. Something like that. That's visible. Okay, about 0.4 to 0.7. So when we look at, we can the wavelengths, and also we can look at the energy because energy is Planck constant and frequency. So frequency is related to the wavelengths, so that we can calculate energy. Energy is about this is about, but I don't know accurate. This is about the energy of visible energy. Okay, so then diamond. When we look at the diamond absorptivity, the energy, this is the energy 5. The peak is about 12. So it's this is increasing. This is energy is increasing. So is opposite of 5. 5 is about here. 5 is about here, and the 10, 12 is about here. So it's opposite. So what we can see, absorption is something is decaying. 5 is about here. So this is a so high wavelengths about diamond. So the light is, there's no absorption. Is a diamond is it turns out the band gap something is related, valence band and the conduction band, valence conduction band, the valence band. This is 0, and this is energy. So the this is a band gap. Energy gap is 5.47, turns out, electron volt for band gap. So this is the what happened, 5 here. So its electrons cannot absorb. If light is coming, is cannot absorb. So the light is no absorbed and passing. That's what happened. I don't know. You kind of this is diamond. Okay, so light is not absorbed and no reflection. That's why diamond is invisible, transparent. Okay. I think another problem is copper. Which one is copper? Yeah, copper. No. 125. The copper appears reddish. Why? The peak, it turns out 2.7. Copper is a very. This is a typical silicon absorption coefficient. It's a related to electron. I told you the band structure, band diagram is related to the absorption. So a lot of study about the absorption coefficient. The silicon is absorbed. This is about the visible again. 4 point. This is visible. This is visible. So it's okay, but still, the the sun spectrum is something like that. So this is visible, and silicon is only here is absorbed. From here is not absorbed. Is a waste of energy. This is the sun spectrum. So yes, we observe high visible, but we are missing silicon is not perfect for solar cell nature. Okay, I think the other gallium arsenide is a little better. So absorption and copper is very weird. Absorption is so weird about the 3 to this is a nano, so 0.3 is peak, 0.3 is peak, 0.3 is peak, and then drops. So actually it is the blue is absorbed. Blue, about the blue is absorbed. That's why the reddish appears. Once the blue is absorbed, then yellow reddish appears. That's why copper, what happened because of that. This is a property of absorption of copper. Okay. So energy, we understand energy and the wavelengths and the frequency and the electrons. So the photon, once is a photon, if observed, is appears dark. Silicon, it look like dark once it's observed, the light. Okay, silicon look like a dark color. So we can explain the colors of materials and absorptivity, solar cell, something like that. I don't know. This is a kind of we try to understand. I think you can look at it. The solution. I'm gonna post it. The obviously Fermi energy. You have to look at it and let me see what I think 635 is obviously we like to look at it for the midterm binary. This is a early version of bismuth telluride. These days they put something else and improve, but the very early version, bismuth telluride, is mostly used. Early material of p-type semiconductor. We understand that at the room temperature, which is doped at the carrier concentration 1.1, 10 to the 19. I think you can raise a question if you have any question. Okay, any question you can raise, I can answer. So far, okay. The concentration, we know that the holes or electrons, well, we mostly discussed the electron, but you can imagine the opposite holes also, almost the same. You know, charge is the same. We don't have to. I don't have to explain. Is the opposite. So electron or holes usually Usually, when the light energy comes and touches material, if the energy is good enough, it should be good enough, then the material electron can absorb. Okay, absorbed means electron jump and holes moving. So one electron, one holes, and then the light disappear because light is absorbed. I think you have to understand. The light energy is we call photon since the Einstein. It's a wave, but a particle. That's why we name it photon. So definitely energy of frequency and Planck constant. This photon's very specific energy required to make one electron free. Okay, then it's absorbed. Okay, it's absorbed. But typically one electron, one holes, and then it become combined, and then light is coming out again. So light absorbed or light is coming out. Yes. Do you have a question? Okay. So there is no gain. Once the one electron, one holes and combine, nothing happen. But by doping, we just create one of them, electron or holes, not the pair. So we can create the electron and then we can use thermoelectric. The same as holes, we can create the holes and we can use and then generate the power. Okay, that's why we need a semiconductor. Semiconductor do that by doping. So this is, we understand the concentration of holes, 10 to the 19. Okay. Most of, I will tell you, silicon, just intrinsic. There are, I think, about 10 to the 23 atoms per cubic centimeter, usually. So 19 is huge, but still much less than the atom. Okay, so this is about the 10 to the 23 cubic centimeter. Okay, and that's why we understand concentration having the degeneracy of valence band is 6. Anyone rephrase what is the degeneracy of valence band is 6? Anyone? What is that? Some students able to answer this. What is the degeneracy of a valence band? No one? That's not a good sign. Okay. The degeneracy is the number of valleys. Okay. I told you there is a conduction band, a valence band, and so that the electron can be free. This is conduction band. So that we can number of concentration, number of electron, but there could be more than one valley. Okay, so there is an electron is available. Each valley has an electron. So this is a degeneracy. Degeneracy. Okay, is a number of valley. Number of valley. It could be holes also the same. More than one. I think. Yeah, I need to explain a little bit about that.
I don't really understand the concept of valleys. What that
That's a
question's off
degeneracy.
beat.
Yes.
Valleys or degeneracy?
Yes. So we call degeneracy is 6, which means 6 valleys. Okay.
But then what's like
Yeah,
you're using valleys to define degeneracy, but then
yes.
you're defining
Different name of valleys is a degeneracy.
so what are valleys then?
Same. Different name. There's a number of different names. Okay.
No, so what's degeneracy then?
We call it. They call it if there are more than one valley, then there is a degeneracy. They just name it. Okay, don't ask me why. They are using different terminology for degeneracy. There is another name. The chemistry actually they use. There is a number of degeneracy meaning. I'm sorry, but they are using very confusing. One way is valleys. That's the what you have to understand. I had here some example of my, oh yeah, band structure. Band structure, yeah. Yeah, something like that. Once we have a band structure, we can see degeneracy. Okay. Sometimes we can see that. Okay, now where I, yeah. Okay. I'd like to back to you now. So we have 6 valleys, and the density of say effectiveness is 0.6, which means the electron mass is given, but the density of state, effective density of state, we call a star D. We like to relate. So this one is 0.6. This is experimentally, numerically physically they have obtained. So we have to understand that this is real. This is just isolate electron, but the real is different story. That's why they have a 0.6. So density of state effectiveness of 0.6 of electron mass. It is known that acoustic phonon scattering, usually there are three mechanisms. One of them is acoustic phonon scattering. Use R is minus half. They say is dominant mechanism. Okay, so for relaxation time. Okay, I like to go back and look at the relaxation time. A, I think A or V. Yeah, no. Yes. There are three, you know, well, in this just fundamental. Okay, this is a very complicated phenomena. The uh, um, the relaxation time is studied. So there are three mechanisms. The first is acoustic phonon, acoustic phonon scattering, phonon uh, electron actually scattering with the phonon. Okay, maybe not today. I don't think so. But next hour, the phonon is very important. It's a vibration, totally. The lattice vibration is very important. I need a couple of hours to talk about phonon. So maybe the idea is vibration, but very small lattice vibration. Once it's a very atomic size of vibration, lattice size, it is something like a particle. It's not a normal acoustic mode. No, it's kind of a particle, very chaotic motion. So we need to study phonon later, but you understand like a vibration. So this is a major scattering. Okay, we were talking about the electron is moving and the collision and scattered. That is the major mechanism of currency, electrical currency. Okay, so this is the key. How we can figure out the time. So this is one of a major reason is we call acoustic, and we use equations. This is turns out that's why we use acoustic is something like constant, and the energy, we usually reduce the energy and minus half. So I'm sorry, this is not we define tower knot. Okay, we just define tower knot. This is tower knot. This is tower knot. Look at that tower knot. So once we have this tower, we can calculate the tower knot, and then we can figure out acoustic relaxation time. And another is polar optical phonon scattering. So we name it polar optical, or something like that, is proportional to energy 1/2. So, this is the um, constant. And then ionized impurity is there is a third scattering mechanism is proportional to energy 3/2. Okay, something like that. This is the constant. So it depends on the mechanism, but the most important is acoustic phonon. This is a dominate. Not always, but mostly dominate. So we assume acoustic, and then we figure out this constant and calculate. We try to calculate. That's what we are doing. Okay. So now that's what we understand. It is known that acoustic phonon scattering is dominant. For relaxation time, the velocity of sound is given. The velocity of sound is 10 to the 5 centimeter. The meters is mass density. Mass density is given, is a kilogram per cubic mass density, and deformation potential is given, and number of degeneracy is 6, and density of state effective mass is it's just multiply 0.6 to the electron. So I think the others are constant, Planck constant, Boltzmann constant, and the electric charge is given. So that the following transfer property are determined at the room temperature using power law. The reduced Fermi energy of these Fermi energy we want to calculate. This is look like a semiconductor, and the Seebeck coefficient we like to calculate. Mobility of the carrier we like to calculate. Electrical conductivity, electronic thermal conductivity, and the dimensionless figure of merit. Dimensionless figure of merit, I think is better. No. Dimensionless figure of merit, GT. Assuming lattice, I think lattice one is lattice thermal conductivity. So K lattice thermal conductivity is 1. Assume we will study next hour after exam. So assuming, and then we like to figure out. So dimensionless figure of merit is alpha square sigma ke plus k lattice. So lattice is given. Once you have three property, you can calculate. That's what we want to compute. So the first feedback from the book for power, the power law. Power law is the relaxation is kind of energy. So we assuming the acoustic phonon. So we use that. Once we use that, according to book, this is coming out. Okay, let's look at it again. Yeah. Chapter B. Yeah, let's go back and look at it. Since we haven't carefully looked at it, I like to look at it now. Again. Okay, we discussed Boltzmann. Everybody, this is one of homework. I think how was derivation of this? I hope somebody say okay. Can you say okay? Some students, or none of you okay? How many students are there? 20 students, yeah. Some students say okay. Oh, nobody say okay. You don't understand what's going. Yeah, that's what one more student say okay. 20 out of, because I showed, you can look at my lecture and the book. Still, you don't say okay. Too difficult? Okay, so we derived the Boltzmann transport equation. This is a Boltzmann transport equation. Okay. So the tau is relaxation time approximation. Actually, that's what we assumed, and we try to figure out the time between the collision. That's velocity and then we um, we look at the definition of density current. Current is number of electron, charge, and the velocity x direction. So that using the definition of concentration, electron concentration, and using the also we have to use the Fermi Dirac distribution. That's the we discussed. That's the distribution of electron. And then this is the we use the Boltzmann. That's the Boltzmann. Okay, transfer. And then we this is the what we have using the density of state. We discussed the density of state and distribution, and then we have a current, and then we have a relationship current and electrical conductivity, with the temperature, absence of temperature gradient, and obviously temperature is out of question for electrical conductivity, and then from that we using these and plug in these, we come up with these, and then we use some approximate relationship for metal, and we come up with these and these. This is a simple model, and also we using a simple model. Even simple model, there's a relation between the electrical and the relaxation time, and so that once we have a electrical conductivity, you can compute. That's sometimes we can figure out, and then Seebeck is defined like that. That's from Boltzmann. That's very important. The Boltzmann relationship. This one. So when we very intensively expand the distribution using Fermi, Dirac distribution, and we come up with this. This is external. So even external electric field, this is electric field. Also temperature, but temperature is a effect of temperature, and then other than temperature effect, this is so important. We found electric field is nothing more Fermi energy gradient. This is Boltzmann's beautiful theory, and we found it. Electric field naturally without the external. No, we don't consider external one. And then the gradient of Fermi energy. So Fermi energy is so weird. It's associated with the electric field. That's why we able to figure out this relation using not this one. I'm sorry. The Seebeck. Yeah, Seebeck. This is a Seebeck. Is turns out with the there's no current, and then there's a relationship. We found it. So electric field over temperature gradient. That's so weird. We like to understand what is the nature of Seebeck. This may tell us the nature of Seebeck is electric field divided by temperature gradient, and then using the current, and the current is 0, and then we come up with these, and more importantly, this is more physical. This is known as a Mott formula, very important. Yes, from that, also meaningful, this is the Seebeck. Once we have equation, oh my goodness, This Seebeck is something property. It is property, temperature, charge, but the density of state more is a proportional density of state, but the inversely proportional to the concentration. Too much electron is not helping. But the house, yes, the house density, so many density, or this is density of gradient with respect to energy. Density gradient, this is nothing more. Density gradient is good. So we were looking for the material with so many house density of state, but minimize electron. Interesting. And then the gradient of density of state is high. That is reason why band diagram, not this one. This is, I don't like it. We try to understand the band diagram of something else. Yes. So this is a band structure. Band structure. So we try to understand whatever magnesium silicide, and we can look at it. At least I'm talking about the P-type hole. How many degeneracy? Anyone? Help me. You just try to count it. Can you count is valence band degeneracy? 1, 2, 3, 4. Say
So
something.
three minimums.
Yeah, at least 3. Look at that. 1 degeneracy, 2. But I think this is dividing by 2. Look at that. So this must be a 2. So at least 3, could be more than 3. So degeneracy is at least 3 or more. Hello, student. Do you have a question? Okay. And this is actually this is they use the zero is here energy, but we usually zero is here the bottom. This is a conduction band. This is a conduction band. So we just analytically use this is the zero, but these guys, they use the zero is here. It's okay. And so definitely this material has a band gap. Yes or no? Answer. Yes or no?
Yes.
Yeah, it look like yes, because this is the 0 hour and then top of a valence band. So this is a energy gap. And the direction is we understand gamma is here at the center, and x direction and L direction, whatever, K direction. So this is the direction. Do you have a question, students? Why? Okay. And this is K-space. This is K-space. If you don't want to question, turn off the microphone, students. Turn off the microphone so that I don't have to hear your voice. Everybody, okay? So K-space, this is we call Brilliant zone of K-space, Brilliant zone. This is very convenient because this is boundary, actually, it meaning the boundary of lattice. So it's a repeating. This is repeating. So once we understand the 1 billion zone, we understand the entire material because the L is K is 2 pi over wavelengths. So small, which means K is large up to the dimension of the specimen. So this is the size, and this is the boundary. So mostly interesting is boundary, not the center. That's why we use a Brilliant zone K-space, and we have a band structure. This is everything. Once we understand this is entire. Now, this is density of state. This is a density of state. The density of state. So this is a Fermi energy. Usually, Fermi energy is something else. We usually figure out Fermi energy, and this is the gap energy band. This is Fermi energy, and this is the slope. This is the slope. This is the slope. The steeper, the better, alpha. So we look at the very steep, because according to the analysis, the steeper, the better, and the n is smaller, the better, and the density is large. Density large is better. Large is better. Something like that. We can look at the material, good material. That's why A or B. Yeah. This is what happened. Okay, now we understand. We understand the Seebeck. This is a very rough, and we assume the matter, but still it tells us something. Now, the better idea is a power law. Now, electronic thermal conductivity, electronic thermal conductivity, actually thermal conductivity consists of electron and lattice. Lattice is later. So now we look at electron. Electron turns out is a defined. This is the electron because the electron is moving, number of electron, velocity, and carry energy. So very easily we can heat flow, and the heat flow is related to the temperature gradient. That's why we're able to figure out the electron, and then this is the equation, and we turns out this L is a Lorentz number, is a constant. Look at that. Turns out for the metal. So in terms of Lorentz number, this is what we found. Electron thermal conductivity is a Lorentz number. This is the law, Wiedemann-Franz law, because of a very interesting law, constant. Anyhow, it depends on the electrical conductivity and temperature, but minus Seebeck. So Seebeck is helpful because GT is alpha square sigma KE plus KL. So smaller, the better. So that Seebeck is higher, the better. Higher, the better. So we learn something from this analytical, but this is a very rough. Anyhow, using the rough, simple, but now power law is more practical. This is the power law, constant, and the energy R. R is depend on the three mechanism, and so acoustic phonon is one of dominate, not always, but mostly, so that we able to figure out. And there are two more mechanism. But I like to, I'm sorry, it's too much side story, but I like to talk about equipartition principle. I think this is somewhat important, students. So we know the energy of electron is mass times the velocity. Kinetic energy is energy. But if you look at carefully, the mass was so complicated, and we use density of state, effective mass. We just so we use that, not the real the mass of electron or particle. So we use these so far, you believe or not. But the air, we like to redefine the kinetic energy here. But this mass is now it's different with the density of state, effective mass, but with we define this is MC, conductivity effective mass, or inertial, some other books, inertial effective. So we redefine here. Anyhow, the particle is physics, is the energy. It's very interesting is we found only temperature, not nothing to do with the mass. So x direction, y direction, z direction is the same. We can say that x, y because of equipartition principle. So once we have that, I don't want to go detail, but it turns out we can come up with in terms of mx, my, mz, the conductivity, effective mass. But usually it turns out longitudinal, or this is longitudinal, and this is a transversal. So transversal is 2 is the same. So 2 or XYZ. This is typical. So anyhow, the energy is velocity we can relate in terms of conductivity effective mass. The question is the relationship between conductivity effective mass and the density. This is so important. Density of state effective mass and density of not the conductivity effective mass, the relationship is question. That is questionable. We had the difficulty to relate these, but definitely two definition. Anyhow, it turns out when we do that, power law, then power law, and now in terms of power law, we have a little different. This is a more elaborate, accurate than the simple model. Okay, so it's related to the Fermi energy. Reduced means nothing. Reduced means energy kBT. That's a reduced. So Fermi, the reduced Fermi energy, and Fermi integral we define. I think a Fermi integral, yes, because it is so often appears. We define in terms of S. S is integral from 0 to infinity energy power to the S. That's the S indicate. Because look at that, the mostly Fermi energy distribution. So that we can express in terms of R, depend on the mechanism, scattering mechanism. Okay, if we use acoustic phonon, fine, we can use it. So in this example, we like to compute the CVEC of lead telluride, and doping is given. This is doping, and the density of state is given 0.12. You understand that now, and assume acoustic phonon. No, acoustic phonon scattering, assume dominant. And what is determine the CVEC coefficient. So we look at this equation, all we need is Fermi energy and Fermi integral. So Fermi energy is the key, how we can get the Fermi energy. But if you this is the power law concentration. So from that, if we know the Fermi integral, this is known. Look at that. This is a concentration given. This is degeneracy given. Density of state effective mass is given. Kb is constant. Temperature is given. H is given. So only unknown is Fermi energy because integrate. That's why we like to look at the appendix. Okay, appendix F. Appendix F, the book. There are two tables. F1 is this. That's what we are looking for. There is another, but later. So this is look at that S So that look at the table. What is a table? Is if we know the S, if we know the S, the Fermi integral, we can find the Fermi energy. Ooh, that's so. Do you understand? So if we know this value, then we can find the Fermi energy. Again, if we know the S value, then we can find the Fermi energy. Okay, now let's look at it. What was AP? Yeah, here, when we transfer this to the left side, and everything transfer, and this is known value, I can get the 2.761, all this value. That's the Fermi integral. So if Fermi integral is 2.7, what would be Fermi energy? 2.76, 2.76. Where is my appendix? The S is, I think, I'm sorry, what was the S? Anyone remember? Huh?
The Fermi right now.
S is what? You tell me. What is the S? You read it. What is the S?
So it's just the exponent, just a half.
Yeah. S is 1/2. So that half, and what is a 2.7? 0.27. I'm sorry. Ah, Jesus. I have a very bad memory. 2.76. I'm sorry. So 2.76 is around here, 2.6, 2.76 and a half. So this is the somewhere value is a Fermi. No. 2.76 here. 2.76. 2.76 is here. I'm sorry. 2.76 is here. The Fermi energy is 2.2. Fermi energy 2.2. That's what. Yes. Fermi energy 2.2. Actually, from the table, I just got it. Fermi energy. Once you have Fermi energy, then you can compute. You can compute everything. You can use Fermi energy, and you can compute everything. You can compute these, compute these. This is a 2.2, and this minus 106. What is a minus means? Anyone? Some meaning of minus. Seabed. Come on.
Is it the direction of flow of energy?
No. Somebody else. That's very fundamental. The CVEC, if CVEC turns out to be minus, then what does it mean? Hmm? Please join us. This is the middle of a course. You cannot answer this. This is not good. No one. So you don't care plus, minus, whatever number. That's not the good. This minus meaning is electron. So it's n-type. N-type CVEC. Phonon holes is p-type. This is a plus. This one is a plus. So that we talk about the electron and okay. Anyhow, so we compute the CVEC is 106 micron volt K. Okay, and once we have using the semiconductor equations, and then using the, I think the rest is everything plug in. It's a 0.029 Fermi. So what is a 0.02 meaning now? Our the coordinate, I told you this is 0, bottom of whatever. This is electron n-type. Okay, and this is a valence. This is a valence band. This is a conduction band, and this is a gap. So 0.029 is Fermi is about here, Fermi energy. So sometimes it is a minus. We like to have somewhere here, but it's okay, close to. Once Fermi energy, then you know what happened is this is density, and this is Fermi energy in this case. So that this is the electron. Still, it's okay. Okay, something what happened in this case. We understand that and so you can do the same things with electrical conductivity, and this is the redefine the Lorentz number redefine, and you can calculate. Once you calculate, and then you can calculate the electronic thermal conductivity. You can calculate, and density, electrical conductivity. You can calculate using electrical conductivity. You can use whatever this. once you calculate the Fermi energy, again, you have to figure out the Fermi energy, and then you can calculate the electrical conductivity. And then the T naught is, you have to look at the, I think, acoustic. If you look at acoustic, I define the T naught energy, acoustic phonon. So you have to look at the definition of tau naught. So that's the tau. We assume tau is acoustic. You can use and calculate. So you need, I think, where is it? Yeah. I think you need to calculate the tau naught. Yeah, once you have tau naught, you can calculate. In this case, you can use. The others are given, and you need the Fermi energy. MC is, you have to assume, if you don't know, I think MC inverse, what was, I think you have to look at the definition of MC here. MC is 1/3, 1 over longitudinal, 2 over, but I think if you have a question about, then you can use, everything is same direction. What is, you can assume cubic, same direction, and MC star is, I think you can assume the MD, and then MD is whatever depend on the ratio which is given. That's the assumption. Yeah, density of state is given 0.12 electron. But if you assume MC, MD for, you can assume this is what they call the cubic isometric material. You can assume. Actually, really is not, but that's the one way we assume. So that you can use it and calculate. I think, did I mention that somewhere? Yeah, we use that. Okay, now, so I think this one is, you should know when we summarize the dimensionless figure of merit, it depends on the beta. Depend on the beta. So turns out, so what is a beta? Is this. This is the beta. And when we plot ZT in terms of reduced Fermi energy, and also depend on the beta. So this is a really characteristic of material general. Obviously, we assume the scattering, but most of material is somewhere between here and here. So 0.03 something most of. So when we look at this, nothing, maybe degeneracy higher the better, beta. This is nothing we can do effective material prop. Effective mass is nothing we can do. And then temperature H, nothing we can do, temperature. And tower maybe, but it's almost, yeah, assuming acoustic phonon. But here is MD, 3/2. The others are constant. MC, effective mass. Look at that. So this is again MD, MC, MD, 1/2. So this is something related to the beta. That's what I found. So once we figure out the density of state effective mass over conductivity effective mass, that might be related to the beta. Okay, that we'll discuss later, not today. Okay, but I like to indicate. So let's go back back to the problem now. What was problem is 3? Yeah. So that again we discussed Cvac is given and the density of state expression is given for power law. And again, we can get the integral constant. And then we found the Fermi energy from the table using half. Why I have this is a minus a half. I think it's something missing. I think here mostly assumption is yeah, is acoustic phonon. So this is error. I think this solution is error. It should be minus. No. S is half. I'm sorry. S is half is okay. But R is a minus. I was confusing. R is a minus. S is okay. So we got the minus 1.8, and then I got the F naught, F1, and plug in, and we compute 334. It turns out plus. What does it mean? Plus. Now you answer. The CVEC turns out the plus 334. What is the plus meaning?
We're describing a p-type semiconductor.
Yes. So it's holes. Okay, p-type. It's okay. It gotta be p-type. This must be a p-type. Let's look at it. Is that the p-type? I don't know. Yes. Bismuth telluride, p-type. Interesting. They used the p-type, so gotta be a p-type. I'm really like to know the name of the student, just answer the P type. Who is the name?
Isaac.
Say again?
Isaac.
Isaac. Isaac. Okay, thank you. And the electation time used, and the tau naught, and the mobility, and the Fermi energy. We got it, and mobility. We can the rest is just to calculate, and the electrical density is calculate, and the Lorentz number for power law, and then this is the thermal electronic thermal conductivity, and assuming lattice is 1, so that GT, I think, yeah, this must be inverse of K, or yeah, G is the inverse of K. I think GT, if you calculate the T, and then there's a dimension is something. Okay. I'm not sure. This is, and the temperature, then we have a dimensionless 300 K. Okay. Those are the midterm coverage. Any question? I'm done today. I haven't decided how many number of problem, but the topics are these. And maybe I can send out some information about the midterm by email sometime. Okay? Otherwise,
So,
yes.
so we're not covering anything from chapter 5 then?
No, not chapter 5. Chapter
Okay.
6.
Okay,
Only
thanks.
only chapter 6. The basic electrons and transport properties. Okay. Thank you. Bye bye.
Is it gonna be during the full 2.5 hours of next class?
Yeah, I think 7 to 10, 3 hours. 3 hours exam. Okay. I'm thinking 3 hours exam because anyhow evening, so you can have no extra schedule. I will announce that at the time. Good luck. Okay. Bye bye.
Bye bye.
Bye, sir.
Bye bye.